I think that you are not. Oh, so thank you, Mariki, for introducing me, and thank you, the organizers, for giving me the opportunity to speak here. It's a very nice pleasure. So what I'm going to talk today is it's joint work in progress with Robert Lawitz from the University of Nottingham, and the idea is try to use his previous paper with Chelsea Walden, who's on the audience, to construct some modular categories using super quantum groups and actually Nichols algebras. So here's the content. Before I begin, I will fix the field, algebraically closed field of characteristic 0. In case I forgot, Hopf algebras are always finite dimensional and tensor categories are always finite. But I will try to recall that every time I need it. So the content is the following. I will start with the motivation for the kind of problem that we want to discuss today. And why not a little bit of history. Then we will move to some generalities of the construction that I'm going to tell you in the first part. First, it's a modularity on monadal centers, which is due to Shimizu, and then we will move to modularities on relative monadal centers, which is due to Lawitz and Walton. And finally, I will tell you something about our joint work with Robert Lawitz. That's almost there, hopefully. So let's begin. The idea is the following. The kind of construction that we want to do is we want to start with some of algebras and construct modular tensor categories. So let me briefly recall what modular tensor categories are. They are fusion, which means that they are tensor infinite and semi-simple. They are also ribbon, which means that you have a braiding and a twist that do something. And you also assume some condition of non-degeneracy of this category, which I don't want to be very precise. So how this arrow here works? Well, it depends. And I'm going to give you some examples of what I mean, of what I don't mean. So the first example is designed to lower your expectations for this talk. What you can do is you can start with Lustig's big quantum group at root of unity. You can take the category of tilting modules, which are certain nice modules, and you can do a construction called semi-simplification to get a modular tensor category, and maybe that's the main family of examples of modular tensor categories. But that's not the kind of thing that we're going to do today. So let's move what we're going to do. If I see this arrow, the first thing that I will try to think is just try to go from one place to the other via representations. So we have this dictionary here. If you start with the Hopf algebra H, you can take H mod, the category of finite dimensional representations. And if your Hopf algebra H is finite dimensional, then you get a finite tensor category. And then you have a dictionary that relates, for instance, semi-simplicity of H with the notion of being fusion for H mod, and so on. If you have the quasi-triangular structure on H, then you get the braided structure in H mod. If you assume that H is factorizable, then H mod is non-degenerate, and you finally have some ribbon conditions being equivalent as well. So that's mostly a dictionary that we are going to use interchangeably. And the idea now is instead of consider H mod, start with H, a finite dimensional Hopf algebra, and consider the Dirichlet double, which is a new Hopf algebra, which is always quasi-triangular and factorizable, sorry. And if H is semi-simple, so is the double. So the idea now is our DH, our new Hopf algebra DH, satisfies all these conditions. So what we want to know now is when DH is ribbon. So that's a classical theorem that took Kaufman and Radford in '93. And they classified when DH has ribbon elements. So you start with finite dimensional Hopf algebra H, and you consider the distinguished group lights on H and H dual. So what they prove is that there is a bijection between the set of ribbons elements of the double and certain square roots of the distinguished group legs. So we are going to treat with sets like this one in the talk, but I'm never going to actually write down what I actually mean. But you should always keep in mind that something like this, you need some square roots satisfying some extra condition, in this case, in the square of the antipode. And so the outcome here is that if you start with H semi-simple, then you know when the H mod is modular. And maybe that's the main idea that's behind the entire talk. That you can assume something on H and prove that the double is modular. So the motivation for the talk is the following. We will forget about semi-simplicity, consider a new notion of modular tensor category, which actually is not new, and try to construct new examples. This problem is not a new one. For instance, Shimizu already considered it and tried to get examples using monoidal centers. So what he did is generalize this theorem and understand when there are ribbon structures on monoidal center of a finite tensor category. Then Lawitz and Walton did the same, but generalized this, considering braided monoidal centers instead of usual centers. And as a consequence, they get very explicit conditions for modularity of certain Greenfield doubles of Nichols algebras, which we are going to introduce now. So the goal of this talk is decide which Nichols algebras of type super A, which is something that we're going to see later, give modular tensor categories. So any questions so far? Hope I'm not going too fast, too slow. Okay, so let's discuss modularity on monoidal centers. But first of all, I need to tell you what our new definition of monoidal tensor category is. It's due to Lubachenko in the 90s. And the idea is a modular tensor category is a finite tensor category, which is ribbon, which means, you have the braiding and twists doing something, and you have non-degenerate conditions there. So this can be seen via having a trivial Mueller center, which is also equivalent to having a certain factorizable condition on the modular center. And this equivalence to Shimizu, but it's not very important for what we're going to do. And here is Shimizu's theorem. So you start with a finite tensor category C, then there is a bijection between ribbon structures on the modular center and certain square roots of this couple of guys. The first one is the distinguished invertible object of C, and the other guy is the Radford isomorphism, which is something that you can find doing some stuff. And you need to have some extra conditions, which I'm not going to write. And I'm going to denote this set, which is vaguely defined, just using the symbol of square roots of the this Radford isomorphism. So as a consequence, you know that the center is modular when this set of square roots is not empty. So a particular instance of this theorem, you can apply this if you start with a pivotal tensor category and you assume it to be spherical, then you get kind of trivially, you get some square root of this distinguished invertible object. And just to be precise, we are in this non-semi-simple setting, so the notion of spherical is not the usual one. What we do now, when you want to consider spherical structures in this non-semi-simple setting, you need to have certain isomorphism between the distinguished invertible object and the trivial object doing something that's written here. This is due to Douglas, Schomer, and Snyder, and this is the right kind of spherical notion that we need to consider, and it's actually going to be useful at the end of the talk. So that's Shimizu's generalization of Kaufman-Radford, and now we're going to introduce another generalization of that, which is due to Chelsea and Robert, as I said before. So the idea is now to start with a braided finite tensor category A, and you consider a tensor category C, which has an acentral structure, which means that you have a nice functor doing something. And if you have this data, you can construct what's called the relative monoidal center. And this is a category that's full subcategory of the monoidal center, of the usual monoidal center, but you only consider objects such that the half braiding is compatible with the structure with the new structure you have. So and this relative monoidal center is useful for us for two reasons at least, and the first one is the following: if you start with A being the category of modules where K is a quasi-triangular Hopf algebra, and you consider the category of H mods inside of A for H Hopf algebra in A, then what you get using this relative monoidal construction is the category of Dieter-Drinfeld modules of H, but inside of A. So this might be kind of weird, but there is a nice Hopf algebra realizing this category. The Hopf algebra is a kind of double, which is due to Majid. And we are going to discuss this later, but it's going to be very useful for our results. So here is the second reason why we really care about this relative construction, and it's the theorem of Lawitz and Walton, generalizing Majid's theorem. And the idea is you assume that you start the category A you started with is non-degenerate, and also some mild condition on the image of the structure functor. Then the relative monoidal center is modular as long as you have some square root of C. So this is exactly Chimisus condition. And so now you have a nice way to decide if these new categories are modular or not. What we want to discuss now is how do you apply this to braided Drinfeld doubles of Nichols algebras. So let me tell you something about these Nichols algebras. The main idea is the following: you start with a matrix Q, just consisting of non-zero scalars, and what you can do with this Q is construct a Nichols algebra. So it's a graded and braided Hopf algebra. And here by braided, I don't mean braided inside certain category. I just mean braided in more classical sense. And what's remarkable about these Hopf algebras is that there is a classification of which matrices Q give finite dimensional Nichols algebras. And moreover, there is a recent organization in Lie-theoretical terms, which is due to Andruszkiewicz and Antiono. The idea is that they took this classification here, which is a family of tables, and they find a nice classification. So they put it in 4 or 5 classes, but for us it just will be enough. And the idea is you have this Cartan type family, which are related with Frobenius inductive kernels. We are going to say something about this in a little bit. And then you have super type, which are related to contragradient Lie superalgebras in complex numbers. And these are particularly interesting for this talk. Then you have the supermodular type, which are related to contragradient Lie superalgebras in positive characteristics. And by the way, this equivalence requires some new knowledge on this kind of Lie superalgebras, or at least I think it's new. And finally, there's this UFO family of unidentified Nichols algebras, unidentified in Lie-theoretical terms. So what you can do with the Nichols algebra is the following, or what we want to do here is the following. So you start with a Q such that the Nichols algebra is finite dimensional, and you consider a finite abelian group, which I'm going to write like this, which admits certain characters. And what you need these characters, you need that these characters have these values in your generators, and consider K to be the Hopf algebra, the group Hopf algebra of G. So if you are an equals algebra person, what you usually do now is, if you have this data here, these characters, then you can realize your equals algebra as a Hopf algebra in the category of Dirichlet modules over G, or over K, the group algebra. And if you want to get an ordinary Hopf algebra, then you take Bosonization by G and you go back to the non-braided world. But instead of that, what we're going to do here, or what Walton and Lowitz did, is you consider the equals algebra as a Hopf algebra in another category, which is the category of comodules over K, which is just G-graded vector spaces. But you need to consider certain air matrix here. And by doing that, what you can produce now is a new Hopf algebra, which is called the braided Dirichlet double. And just to say something quick about that, we like this because you only have one copy of the torus here. And usually if you do this kind of construction and then take double, you end up with two copies of the torus. And this can be problematic for some reasons. Okay, let's say something about why all these symbols are useful. Suppose you start with a irreducible Cartan matrix, and you take this symmetric matrix, the DIs, and you fix a root of unity Q. This seems like the same symbol I used for the matrix, but it's just a number. You start with a root of unity and some restriction on the order, and define these numbers now. So these Qij's give you a braided matrix Q, and this is what's called of Cartan type. So what happens now is you take Bosonization with G, what you get is the quantum Borel of the Lie algebra associated to this Cartan matrix. But if instead of that you take this braided Dirichlet double, what you get is it's a small quantum group, the entire small quantum group. So that's one reason why these kind of algebras are interesting, and this is the most interesting one for us today. So suppose you start with a Q. This is a Q, not an A. So forget about Cartan type. You start with a Q such that the equals algebra is finite dimensional. Then this category of modules over this twisted Dirichlet double, which you can realize as this relative monoidal center, this category is modular if the symmetric bilinear form on G, which is defined by this is very, very common in the equals algebra world. If this bilinear form is non-degenerate, and if the top degree of the equals algebra admits certain square roots. So it looks very similar to Kaufman-Rutherford theorem. Here, this is a non-degeneracy assumption, and this is a square root assumption or condition. As an example, they prove that this Q of G, the small quantum group, is modular, and here you need this restriction on the orders. And also they explicitly check one example of supertype and rank 2. So and the rest of the talk, I'm going to use this proposition several times, but instead of saying that this thing is modular, I will just say that the equals algebra is modular. I'm doing on time. Okay. So far, so good. So let's say something about this equals algebra of supertype A. So we start with a matrix Q, and it's going to be associated with some subset. This is the labeling set of indexes you started with. And you should think of this subset as just a set of odd simple roots in say, a super Lie algebra. And you also fix a root of unity of order 2. If you have these two things, then you can construct what's called a super algebra, an equals algebra of type AGQ. So what we are going to assume here, but it's not necessary for definition, is that the order of Q is even. It's just because to be precise on what I'm going to say later. So, and the goal of the paper I'm writing with Robert is try to decide when these Nichols algebras are modular. So the first thing to do was try to decide when the base category AQ is non-degenerate. And we get a very specific condition here. And as Susan said, this is the kind of example where everything comes down to computing a determinant. So this category is not degenerative, and only if this number here is coprime to the order of Q. And this number here it just depends on this subset of odd simple roots. You have some parity associated with this J, and these are some positive roots of the Nichols algebra, which are not very interesting for this talk, but something that you can do. And so using this, we could prove the following. So you start with the Nichols algebra, and you say you can see it as a Nichols algebra inside of AQ, and there you take bosonization and get the Hopf algebra. So this Hopf algebra is spherical if and only if every simple root is odd and the rank is even. So that's the first nice result. And we also have a formula for the pivotal element that determines the spherical structure. But I'm not going to write it here, of course. So using this, what we conjecture, and we are almost there, is that this relative Greenfield double admits a Ribbon structure if and only if the same that happened here. So if and only if every simple root is odd and the rank is even. In this case, we think that there are this number of Ribbon structures, and only one of them comes from this spherical structure that we constructed above. That's all. Thank you for listening.